Okay, so let's talk about thermochemistry. That's a topic that we'll be dealing with in chapter 6. So, what's thermochemistry? Well, thermochemistry is that area of chemistry which deals with energy changes in chemical reactions, right? So, what we're going to look at first is the definition of energy and what it means and the different types of energy. And as you can see here on the screen, that the definition of energy is the capacity to do work. So this begs the question, what do we mean by work? Well, work is said to happen whenever force is applied to an object and the object moves, right? So if you push on something or if you pull on something and it moves, then it is said that you have done work on that object. Now, if you apply force to an object and it doesn't move, it doesn't matter how big the force is, if it doesn't move, then no work is done, all right? In terms of what energy literally means, it means work within. However, it is not possible for an object to contain work. It can contain energy, but not contain work, right? And in terms of the different types of energy, you have two types. You have what is known as potential energy, which is the energy an object has by virtue of its position or composition. And then you have kinetic energy, which is the energy an object has by virtue of its motion, right? So anything that moves has kinetic energy. And here's a formula that we use to calculate kinetic energy. EK, kinetic energy, is equal to half mv squared, where m is the mass of the object that is moving, and v is the velocity or speed of the object that's moving. And the units of energy, according to the SI system, is the joule unit, symbolized by the letter J, and that unit is also a combination of other units we know before, kilograms times meter squared over second squared. And you can understand that based on the formula here. Let me just get to my writing function here. So according to the formula, kinetic energy is equal to half mv squared. Now, if mass is in kilograms and velocity is in meters per second, that means that when you look at how these terms are arranged in this equation, then the unit of energy would be kilograms meter squared, over second squared, which is the same thing as the joule unit, right? And this is something that we met before in the previous chapter when we were talking about different values of R, but I won't go into that. I won't go back to that again. But basically, this is basically the unit of joule, which is the same thing as this combination of units. Okay, so some terms that you need to know about in thermochemistry. As we said before, thermochemistry is a study of energy changes that occur in chemical reactions, all right? And almost all chemical reactions involve some changes in energy. Now, some other terms that you need to know about, when we refer to the system, we're talking about the part of the universe that we're being studied, especially when it comes to looking at energy changes, all right? So that part could be anything. It could be a test tube, it could be a beaker, it could be a huge reaction vessel, it could be anything. But basically, we're talking about the part of the universe that we're focusing on in terms of examining the type of changes taking place, both in terms of chemical reactions, or maybe not even chemical reactions, but if energy changes are taking place, that's what we're concerned about. And then the surroundings would be the rest of the universe, right? So very often we can simply write down the relationship between system and surroundings. We can say that system plus surroundings is equal to the universe, right? So that's basically showing you the relationship between the system, surroundings, and the universe. Okay, so let's talk about different types of systems. As we said before, the system is that part of the universe that we are studying, right? And there are three types of systems. You can have what is known as an open system, where energy and matter can be exchanged between the system and the surroundings. Excuse me. We can have what is known as a closed system, where you can have energy being exchanged between the system and surroundings, but not matter. And then we have what is known as an isolated system, where you cannot have either energy or matter exchanged between the system and surroundings, all right? So we're going to talk about the differences between these systems in some detail later on, but for now, this is basically some introductory terms in relation to the different types of systems, all right? So in terms of a closed system, this is what this represents. This is basically a bottle of, it looks like honey. As you can see, it's closed, so therefore there's no exchange of whatever is inside here with outside, right? So there's no exchange of matter between the system and surroundings, but you can have energy flowing into or out of the system. So you can actually heat the entire system from the outside, and that energy will flow into the bottle and therefore heat the contents of the bottle. Or if you cool it, you can basically, by doing so, remove energy from the bottle, so therefore the energy flow will take place from inside to outside, all right? So that's basically what you're looking at here. This picture here, which is also represented by this diagram, is a closed system, all right? So that's the point being made here. Now, a question is being asked here. It says, after the lid of the jar is unscrewed, right? So let's say you open this up. What kind of system is it? And the answer is simple. It's an open system, because now you can have exchange of matter and energy between the system and the surroundings. So, you know, air can enter into it, for example, and that could affect, you know, the type of energy changes that would take place, for example, all right? Okay, so let's talk about internal energy, which is the total energy that is contained within a system. And you can actually categorize two types of energy that would make up the internal energy. Now, part of it, one type of energy that's a part of the internal energy, is the kinetic energy, which we said before is the energy objects would have by virtue of its motion. Now, at the microscopic level, we're dealing with the motion of particles, atoms, molecules, etc., right? And when it comes to kinetic energy at that level, you can have energy due to translational motion, rotational motion, or vibrational motion, all right? So translational motion, of course, is where the particles are moving in space in straight lines. Rotational motion is where the molecule or the atom is rotating around a particular axis. And vibrational motion, this typically occurs in molecules, of course, where you have bonds between atoms, and basically you'll have the atoms or ions, if you're dealing with ionic compounds, they are vibrating around a mean position, all right? So collectively, these are sometimes called thermal energy. So the thermal energy is related to kinetic energy, all right? Which is the energy of molecular motion. And then we have the other part of internal energy, which is potential energy. And that's the energy which is a result of forces of attraction that exist between bonds and atoms, all right? And very often we call these energy, or this type of energy, collectively chemical energy, right? So thermal energy is related to the motion of particles. Chemical energy is related to the attractive forces that exist between atoms and molecules. All right, so let's talk about another term that we're going to be meeting a whole lot in this particular chapter, heat. What is heat? Here's the definition of heat here. Heat is the energy transfer between a system and its surroundings caused by a temperature difference, all right? So if you have two objects that are at different temperatures, one is at a higher temperature than the other, and they're connected somehow, then basically what you'll have spontaneously, without anything being done to it, what you'll have basically is the heat energy transferred between the hotter object, or moving from the hotter object to the cooler object, right? So that energy flow is the heat flow because, or the, because of the temperature difference, right? So that's what heat is. Heat is the energy transfer that occurs between a system and surroundings caused by a temperature difference. And here is an example, a hypothetical example of how this thing works. So we have a thin hypothetical wall, and separating that wall is on one side the surroundings, which contains nitrogen gas, and the other side, which contains argon gas, right? Argon gas will be a part of the system. Now, in this particular situation here, provided that basically in this particular situation, the argon gas will have more energy because the temperature is higher here. So therefore, what they will do is hit the thin hypothetical wall, And the result of that is a transfer of energy to the nitrogen molecules on the other side. So basically, as a result, you're going to have the energy transfer or the heat flow from the hotter system to the cooler surroundings, all right? So that's basically what happens when you have the transfer of heat from one object to another. Now, this heat transfer will take place until you reach a stage or a state which is known as thermal equilibrium. And thermal equilibrium is said to occur when the temperature of the system and the surroundings reach the same temperature. So when that happens, the heat transfer will stop, right? So the only reason why you have the heat transfer or the heat flow is because there's a temperature difference, right? Once the heat flow continues until the temperature of both the system and surroundings are the same, then basically there'll be no more heat flow taking place, and the temperatures would be the same for both the surroundings and the system. Now, here is a question being asked. How do the root mean squared speeds of argon and nitrogen molecules compare at the point of thermal equilibrium? Now, this has to do with an equation which we met before, and let me remind you of what that equation is. That equation is, let me see where I can write this. Let me try writing it here. That equation is the root mean squared speed is equal to the square root of 3RT over M. Remember that equation, right? We use this equation to calculate the root mean squared speed of a gas, all right, where T is the temperature and M is the molar mass. Now, what this question is asking is how do the root mean squared speeds of argon atoms and the nitrogen molecules compare at the point of thermal equilibrium? So basically what they're saying is that at the point of thermal equilibrium, the temperature for both gases would be the same. So what I'm going to do is write something here. Okay, so what I'm going to do is I'm going to get out of this, and I am going to open up this here, and let me get rid of that. Okay, so what the question is asking is comparing the root mean squared speed of argon, to that of nitrogen. And if you remember, if you're making such a comparison, then the equation basically comes down to, this ratio basically comes down to the square root of the molar mass of nitrogen divided by the molar mass of argon. So in the case of nitrogen, the molar mass is 28.02 AMU, or that's the molecular mass, same thing numerically. And the molar mass of argon, let me look that up, is 39.95 AMU. And all we have to do is the math here. So let me get my calculator. So that would be 28.02 divided by 39.95. And then I find the square root. So the answer I got is 0.8375, right? So basically the ratio of the root mean squared speed of argon to that of nitrogen is equal to this value right here, 0.8375. And basically what that means is that argon molecules will travel on average at a slower speed compared to nitrogen, which makes sense because after all, nitrogen is lighter because its molar mass is, or molecular mass is 28.02, whereas argon is heavier because its molecular mass is 39.95 AMU. Okay, so that answers the question that is being asked in the PowerPoint here, all right? Okay, I'm going to stop this video here, and the next topic we're going to talk about is the concept of work, which we touched on earlier, but we're going to look at it in more detail, especially as it applies to changes with respect to gases. All right, until next time.